Definite integrals. So far, we've talked about antiderivatives and indefinite integrals, and then we made a jump to discussing area under a curve. So right now, we want to get into a formal definition of what it means to be a definite integral and tie in the ideas that we've covered so far. So just like for derivatives, we had a formal definition of a derivative. It was the limit of a difference quotient, and it took a little bit of work to understand the meaning of the formal definition of the derivative. So we're going to have a formal definition for a definite integral, and we're going to start by needing to define a Riemann sum. So a Riemann sum is a rectangular approximation for the area bounded between a curve and the x-axis with the property that the width and the height of each rectangle can vary. So a Riemann sum here is defined as the sum of I equals 1 to n of f of c sub I delta x sub I. So here I'm not going to get too specific about this formal definition. What I want to do instead is a graphical representation of what this definition says here. So what it says is that a Riemann sum is a rectangular approximation for the area bounded between a curve and the x-axis. So let's draw one such curve. So let's just do a little bit of a sketch here. So let's say we have this curve here, and we're trying to determine what the area is that's bounded between this curve and the x-axis. So something that you might notice that's different from the previous section is in the previous section we made an assumption. We said that the curve had to be positive everywhere, or over the interval we were interested in. Well, here now I've drawn a curve that's negative or below the x-axis, and then it switches to above the x-axis. So a Riemann sum, it's okay for a function to be above or below the x-axis. So we're still thinking about area, but now area can be below the x-axis. So this Riemann sum that's going to help us approximate the exact area tells us that we can use rectangles that have different widths and different heights. Each one can have a different width and different height. So in the previous section, we used rectangles of equal width every single time. And then each of the heights was determined by whether or not we wanted to use the leftmost endpoint on the subinterval, the rightmost endpoint, or the midpoint. So now what we're going to do is we're going to create a bunch of rectangles of any width we want. And we're going to be able to choose any height we want. So let's just say we're considering the interval from A to B. And over this first rectangle, over this first subinterval that I'm going to draw, let's say I make it a width of this little amount here, I can choose any point I want, any point at all between this subinterval to determine the height of my function. So let's say I pick the right endpoint. So I'll go to the function at the right endpoint, and that's going to determine the height of my rectangle. So now I have all this extra area here, but that's the rectangle that I wanted to choose. So now over the next width, well, let's make this next rectangle a little bit wider. So now the width is going to be different because I can choose to vary the width and the height of every single rectangle. And now this time, let's not even choose an endpoint or the midpoint. Let's just choose a height randomly. So the height of the function somewhere between that subinterval. So let's say right about there is going to be the height of my next subinterval. So in choosing my own width and my own height, well, now in this next rectangle, I've only had a little bit of a under approximation here because I'm missing this little portion right here, but it's still a pretty good approximation. I'm still getting all this area that I want to include. So how about the next one we make really skinny? We'll say it's just this little tiny width here, and I'll define the height to be a right endpoint again, and say this is all of my area. So right now I'm missing this little bit of area and this little bit of area, but I overcompensated for this rectangle here. So with the flexibility to choose the width and the height of every single rectangle, I can then make an approximation that's really, really good. So I'll just keep going kind of randomly over here. So I'll make this one a right endpoint again. This one I will just make some random height. And we'll kind of keep going. Let's make this width have a height right here. And this one will go here. and then this one maybe right here. So now I have this collection of rectangles to help me form an approximation of the sum of the area bound between this curve f of x and the x-axis. And the way that I've drawn it, it looks like maybe I'm, overcompensating for area here, but I missed a little bit here, so this would be a pretty good approximation. So the definition of a Riemann sum is just a collection of rectangles that I use to approximate the area, but I can choose any width and any height for each of the rectangles. So this formal definition here, this f of c sub I, delta x sub I, well, just means that c sub I is any point in each of the subintervals, and delta x sub I is any width. So this f of c sub I is any height, and delta x sub I is any width. So each of these are areas of rectangles, and this sum means I'm adding up all those areas of rectangles. So what we've done in the previous section, right, left, and midpoint approximations, all of those were special cases of Riemann sum approximation. So a Riemann sum is really the general way to add up all of the different rectangles that accumulate all of the area underneath the curve, but it's so general that I can vary the width and the height. But it did turn out to be a little bit easier to do when each of the widths was the same and we chose a uniform height every single time. So now I want to keep this little rough sketch picture here and define what it means to be integrable in a more formal way. So a function f of x is integrable over ab if all of the Riemann sums, not just the endpoint and midpoint approximations, approach the same limit L as the width of the largest rectangle approach 0. So here's what's going on here. So each of these heights were some f of c. So f of c sub 4 maybe, and this one was f of c sub 3. So all of these are different heights, function heights. That's the f of c sub I part. Each of these widths here are delta x sub something. So delta x sub 2, and this one's delta x sub 3. They would go in order, but as you can tell, each of the delta x's represents a different width, and each of the f of c sub i's represents a different height. Well, we say that a function is integrable if the largest width approaches 0. So in this case, I've tried to draw one so that the largest width is evident here. So here's my largest width. So I'll just call that, how about delta LW? So the largest width, LW, if I can make this width approach 0, so if I can make this width really, 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 really thin, then I'm going to get a better and better approximation, so much so that if I make them approach 0, I'm going to get an exact area under the curve. So if this limit exists and it equals some number L, then the function f is said to be integrable over the closed interval from a to b if all of the Riemann sums. So not just the endpoint and midpoint approximations. And we took a look at this in the previous section. This was the last theorem where we said the limit as n approaches infinity of r sub n, and the limit as n approaches infinity of L sub n, and the midpoint approximation. All of those, if all of those were some limit L, then we ended up getting the exact area under the curve. So we're generalizing that even more by saying that if we use any type of rectangles with any width and any height, and if we force the width of the biggest one to go to 0, well then all of the other ones must go to 0 as well. So that's going to give us an exact area that's trapped between a curve and the x-axis. And if this limit exists, then we can say the function is integrable. So there is some detail that I'm leaving out here. It's just a broad overview of what it means for a function to be integrable, and just an introduction to what it means to be a Riemann sum. So if you ever decide to study math, this is a big topic that you would cover in higher level math classes, but for now, I just want you to understand the idea that we're trying to find the area under a curve exactly, and we're using this notion of limits. And we're using it in the most general possible way. So not just right, left, midpoint approximations. If we have any width and any height rectangles, if we force the biggest one width to go to 0, then we're going to get that exact area trapped between the curve and the x-axis. So now we can define a definite integral. So the definite integral of f of x over the closed interval from a to b is the limit of Riemann sums. So the notation that we're going to use, and you'll notice it's similar to the notation for an indefinite integral, but now we have these two, what will be numbers, next to the integral sign, and these are called limits of integration, and we'll write that down in just a second. So this is the integral from a to b of f of x dx is equal to the Riemann sum. So that was the formal definition we just looked at of what it meant to be integrable. So I can say that the area trapped between the curve f of x and the x-axis between a and b equals the limit of the Riemann sum, which is some number L. So this is my formal definition of a definite integral. Just to look at some notation, this is read as the integral of f from a to b, or we can say the integral from a to b of the function f. And everything stays the same as far as title goes. This is still the integral sign. And f of x is still the integrand. Dx is still the differential. But now a to b, or a and b, are called my limits of integration. And they're going to correspond to the endpoints of the interval. So a being the smaller number and b being the larger number. So in the past, when we were asked to approximate the area between 2 and 4, a would be 2 and b would be 4. So now the endpoints of the interval become our limits of integration. Alright, now let's take a look at a graphical interpretation of the definite integral. So first we need to know what it means to be signed area. So now that we have curves that we're going to consider to be below the x-axis, we need to think about what exactly are we trying to find when we say we want to find the area bound between the curve and the x-axis. So the area above the x-axis we consider to be positive area, and the area below the x-axis we consider to be negative area. So the graphical interpretation of the definite integral means that I'm interested in the signed area. So I'm assigning a sign to the different regions that are bound between the curve and the x-axis. So any area enclosed that's above the x-axis, I'm giving it the sign of positive, and any area that's bound between the x-axis and the curve below the x-axis, I'm giving it a sign of negative area. And then I'm interested in the signed area because I'm thinking about all of the area above the x-axis, and then I need to get rid of all of the area below the x-axis, or subtract the area below the x-axis. So here, let's just do some colors to represent what's going on here. I'm interested in all of the area above the x-axis, so let's make that yellow. And then I want to subtract from it all the area below the x-axis. So I'm thinking about the area below the x-axis as negative. So if I shade in this region, and I wanted to consider the signed area between this function, so let's call this function f of x. If I wanted to consider the signed area of this function f of x on the interval from 1 to 6. So I don't know exactly what that number is, but looking at the colors, there's more yellow area than there is green. So all of this green, I can imagine, would cancel out the equivalent amount of area in the yellow, but there would be more yellow left over. So when I think about this graphical interpretation of signed area, it's all of the area above the x-axis, so yellow, minus all the area below the x-axis, so in this case green. So we want to go back to the definite integral notation. So the integral from a to b of f of x dx is the signed area of the region between the graph and the x-axis over a to b. So in other words, this graph that I see here, I can represent the area shown in yellow and green as the integral from 0 to 6 of f of x dx is the same as the area represented here by the yellow and the green portion. So I know that this integral has to be some positive number because there's more yellow than there is green. So there's more area trapped above the x-axis than there is below the x-axis. So I want to stop for a quick second and do a recap. So I want to take a look at the big themes that we've covered so far in this class. So the first one is the notion of limits. So we said we needed limits to tie everything together, and informally we defined a limit as the y value a function approaches as we approach some x value from both sides. And then we jump down to defining a derivative. So when I say derivative, the first thing I want you to think of is the slope of a tangent line. But it's also an instantaneous rate of change, that's its application. And then formally we defined a derivative as a limit of a difference quotient. So there's that need of the concept of limit to define a derivative. Well, then we switched gears and we wanted to think about how do we undo derivatives. And that formally is called the indefinite integral, or the general antiderivative. So the indefinite integral, or general antiderivative, well, that was a function. So if I wanted to find the antiderivative of cosine x, the general antiderivative was sine x plus some constant, which is also a function. And then we switch gears, started talking about area. And that takes us to the idea of a definite integral. So when I say definite integral, the first thing I want you to think is this signed area under a curve. So I say under in quotes because we can have this notion of negative area, or area beneath the x-axis, so it wouldn't be necessarily under a curve. But signed area under a curve is what I would want you to think about. And that answer is a number, so it represents an area. So a definite integral, the answer to a definite integral is going to be a number. And formally, we got that definition by thinking about the limit of a Riemann sum. So again, here comes that concept of limits, that tying it all together factor of limits. So we needed limits to define derivatives, we needed limits to define definite integrals. And those are the two main branches of calculus, differential calculus and integral calculus. So let's go ahead and jump into an example. We're being asked to calculate the integral from 0 to 3 of 2x minus 5 dx using the interpretation of signed area. So right now, all of the functions we're going to be asked to evaluate definite integrals of are going to be functions that we can graph and then use geometric formulas to evaluate the area. So this equation is the equation of a line, 2x minus 5. And we're concerned with what's happening between 0 and 3 on the x-axis. So remember that the limits of integration 0 to 3 correspond to an interval. So we're looking at the interval from 0 to 3 on the x-axis. So this dx here and this x variable tells us that these limits of integration are really x equals numbers. So we can erase this for a second. So we're going to draw ourselves a sketch of the graph. And then we're going to use geometric formulas to interpret the signed area. So I'm going to draw a rough sketch here. I'm only concerned with what's going on between 0 and 3. So 0, 1, 2, and 3. And this line has a y-intercept of negative 5. So we'll go ahead and mark the y-intercept at negative 5. And then it has a slope of positive 2. So we'll go up 2 units and then over 1 unit, up 2, over 1, and then up 2, over 1 again. Whoops, that was over a half. So up 2, over 1 again. So this is going to happen at 1. And now I'm going to connect the dots to form my line. But I'm going to stop and I'm going to make it a line segment, because I'm interested in the signed area, so the area that's trapped between the curve, or the straight line, and the x-axis. So all of this area down here is going to be negative area, and then this area up here is going to be positive area. So I can tell automatically by looking at this graph that the answer to this definite integral is going to be negative. There's more area below the x-axis than there is above. So we can erase that now. And now it's a matter of calculating the area exactly. So here, I did do a rough sketch, so I can see that the x-intercept here is going to happen at 2.5. But to find that algebraically, I can just set this function equal to 0. So 2x minus 5 equals 0, or 2x equals 5, and I get x equals 5 over 2 as my 0, or my x-intercept on the graph. So I know that that happens right here at 2.5. So the reason I was interested in this number is because I now need to use geometry, specifically the area of a triangle, to find the area below the x-axis and the area above the x-axis. So the integral from 0 to 3 of 2x minus 5 dx equals, well, the area below the x-axis is going to be negative. So we're going to have negative whatever this area is. So the area of a rectangle or a triangle is 1/2 base. So the base is 2.5, or we'll go ahead and stick with fractions here. So 5 over 2 times the height. So the height of this rectangle is 5. So now I know the area below the x-axis is given by negative 1/2 times 5/2 times 5. And then I need to add the area above the x-axis. So plus, now this base here of this triangle is 1/2, because between 2.5 and 3 is 1/2. So we have 1/2 base, which is 1/2, times height. And the height here of this little portion is up at 1 unit. And I can also check that point that comes out as 1 by substituting 3, the x-coordinate, into the function. So 2 times 3 minus 5 is 6 minus 5. So I get an output, a y value of 1. So I know this coordinate point is 3, 1. So that means the height here is 1. And now it's a matter of adding it together. So here I'm going to have negative, and here I have 25 over 4 plus, and here I have 1 over 4. So I already have common denominators. I can add across the numerator. So I get negative 24 over 4, which is nice. This works out to negative 6. And we said automatically that we knew that our answer was going to be negative because there's more area below the x-axis than there was above the x-axis. So negative 6 seems like a pretty plausible answer for the signed area between 0 and 3 of 2x minus 5. Alright, let's move on to another example. Calculate the integral from negative 1 to 4 of the absolute value of 3 minus x dx using the interpretation of signed area. So here's how I'm going to draw this graph. First, I'm going to draw the line 3 minus x, and then I'm going to make any portion that's below the x-axis flip over and reflect over the x-axis and become positive. So what I'm going to do is I'm going to sketch out 3 minus x. So 3 minus x is going to have a y-intercept at 3. So 1, 2, 3, it's going to have my y-intercept. It's going to have a slope negative 1. So down 1 over 1, down 1 over 1, down 1 over 1. So this here is going to be, and I'll draw it as a dotted function for now, this is going to be the line 3 minus x. Now, I'm concerned with what's happening between negative 1 and 4. So here's negative 1. And then here, if I was really careful, this goes through the point 3, 0. So I'm concerned with what's going on all the way over to an x value of 4. Now, absolute value, what does it do to something? It makes it positive no matter what. So here, this portion of the graph that's already positive or above the x-axis, I'm going to fill it in and leave it a filled-in graph and above the x-axis. But any portion of this line that's below the x-axis, well, what does absolute value do? It forces it to become positive. So I'm going to reflect this portion down here above the x-axis and make it positive. And then it's going to look like what we know to be an absolute value function. So here's my absolute value function. If I want to know exactly what this value is when I substitute 4 in for this height here, well, I can see that it's going to look like 1 because I tried to draw it as neatly as possible. But again, to find this value, substitute 4 into the function. So 3 minus 4, I'll get out the absolute value of negative 1, which is positive 1. So I'm concerned with that number because that will be the height of this little triangle right here. So what I'm interested in finding is all of this area here and all of the area trapped over here. So whenever I take the integral of an absolute value function, my answer is going to have to be positive because absolute value functions by definition only live above the x-axis or on the x-axis, as this one point here indicates. So I'm trying to add up two triangles here. So the integral from -1 to 4 of the absolute value of 3 minus x dx equals, so this first triangle has base, or 1/2 base. So the base here would be 4 units. So to get from -1 to 3, I have to go over 4 units. So base times, and my height here is also going to be 4. So again, to find that value, if I wanted to, I can substitute -1 into the function. So I could get 3 minus -1 in absolute value bars, which is the absolute value of 4, or just 4. So this first triangle has base 4, height 4, and it's positive. So I leave it as a positive number and have to add to it the area of this tiny triangle, which has 1/2 base 1 and height 1. So let's add this together over here. I end up with a 16 over 2 plus 1 over 2. So I end up with 17 over 2 as my answer. So 17 over 2 is the answer to the definite integral of this absolute value function. And just in case you didn't want to graph the function the way I did, if you really wanted to, you could graph this function, the absolute value of 3 minus x, using some translations, but we would have to rewrite it as -x plus 3. So I'm switching the place of 3 and -x, and then I can factor out a negative, so I end up with -x minus 3. And then the absolute value bar would do away with this negative here, so I'd end up with just the absolute value of x minus 3, which is the absolute value function shifted right 3 units. So that's another way to graph this function, if you didn't want to graph it the way I did, by just first drawing the line 3 minus x and then making anything below the x-axis a reflection over the x-axis and making it positive. So entirely up to you if you want to think about it as translations first. Alright, taking a look at another example, calculate the integral from 0 to 2 of the square root of 4 minus x squared dx using the interpretation of signed area. So here, the square root of 4 minus x squared might not look as obvious to some, but this is actually the equation of a semicircle. It's the top part of a circle. So here, if we think about, real quick, the equation of a circle, so x squared plus y squared equals, it's r squared, but let's just go ahead and use 4 because that's what we're going to be talking about here. If I solve this for y, I'll have y squared equals 4 minus x squared. And then I have to take the square root of both sides and include a plus or a minus. So this is an implicitly defined function here. And the positive portion is the top half of a circle, and the negative portion is the bottom half of a circle. So the top half of the circle here, and this circle would have a radius 2 because this 4 is 2 squared, and that defines the radius. So we have from 2 to -2. So the square root of 4 minus x squared, that's the top half of a circle. And the negative portion, -4 minus x squared, is the bottom half of the circle. But as you can see, just the top part, just the positive part, by itself, the one that we're interested in evaluating the area under that curve right now, that itself is a function. So that's the portion we're talking about now, the square root of 4 minus x squared, and we're only interested in what's going on between 0 and 2. So we're only interested in the first quadrant, which forms the shape of a quarter circle. So here, if I attempt to evaluate this integral, the integral from 0 to 2, of the square root of 4 minus x squared dx, well, the area of a circle is pi r squared. So pi, the radius of this circle being 2. So pi times 2 squared, but I'm only interested in 1/4 of the circle. So we're going to have 1/4 pi r squared be the answer. So 4, which is 2 squared times 1/4, is just going to give me out an answer of pi. So the answer to this definite integral here, using geometry and my knowledge that the square root of 4 minus x squared is really the equation of a semicircle, gives me out this answer of pi. Alright, so before we continue with another example, I want to talk about using symmetry to help simplify our calculations. So if we have f of x as a continuous function on the symmetric interval from negative a to a, if f of x is an even function, then the integral from negative a to a of f of x dx equals 2 times the integral from 0 to a of f of x dx. So let's take a look at what that means for a second. So here, when we're talking about a continuous function on the symmetric interval from negative a to a, that means we have to be talking about going from the same number but negative to its positive counterpart. So here, in other words, we're going from, let's say, negative 2 to 2 or negative 3 to 3 of some function, and that function is even. So again, let's take a second to remember what it means graphically to be an even function. So what it means to be even is that I can reflect the function over the y-axis and it looks exactly the same. So let me draw an example of an even function for you here. The absolute value function. So y equals the absolute value of x is an example of an even function because I can take this function and reflect it over the y-axis and it would land right on top of itself. So imagine taking all of the points on this line here and moving them over to the opposite exact point but on the opposite side of the y-axis. So it's a mirror image from one side to the other. And that would be defined as an even function. Now, if I were interested in, let's say, the integral of this absolute value function from negative 3 to 3, so it's that symmetric interval. So if I'm interested in the integral from negative 3 to 3 of the absolute value of x dx, what this symmetric property tells me I can do is instead write this as 2 times the integral from 0 to 3 of the absolute value of x dx. Now that should make sense because if I complete the triangles that I would find each of the areas of, they're the exact same triangle, just flipped around. So this area here, whatever it may be, is exactly the same as this area here, so why do it twice? Why not just find the area once and then double that area? So we're going to have 2 times, well, the base here is 3 and the height here is 3. So 2 times the area of a triangle with 1/2 base 3 and height 3. Well, the 2 and the 1/2 will cancel and I will get out just exactly 9 as the integral I was originally trying to evaluate that had this symmetric interval and it was an even function. So an even function is reflected over the y-axis and it lands right exactly on top of itself. Now, if f of x is an odd function, then the integral from negative a to a, so again that symmetric interval of f of x, is now equal to 0. So let's take a second to remind ourselves what an odd function looks like. I'll draw an example of an odd function. Alright, so an odd function, the easiest one would be y equals x. So if we draw y equals x, this is an example of an odd function. Now, an odd function graphically means that what I can do is I can take this function, I can pick it up, and I can rotate it 180 degrees, and it would land right back on top of itself. So here, if I picked up y equals x and I rotated it 90 degrees, well then it would look like the line y equals negative x. But then if I picked it up again and I rotated it another 90 for a total of 180, you wouldn't be able to tell that you moved it at all. It would land right back on top of itself again. So an odd function has this property that I can pick it up, rotate it, I should be specific, about the origin. So I'm rotating it around this point 0, 0. So rotating it twice of 90 degrees or once of 180, and it lands right back on top of itself. So some other quick examples of odd functions. The cubing function, or x cubed, is an odd function, or even the cube root function that looks something like this. So each of these functions, I can pick them up, rotate them 180 degrees, and they land right back on top of themselves. So these are examples of odd functions. And then let's take a look at this property. If I want the integral from negative a to a, well, notice here, this first triangle that I'm going to create that's below the x-axis, it's going to have negative area of some amount. But then when I go to find the area of this other triangle that's created, it's going to be the exact same area, but all of this down here I consider to be negative area, and all this up here I consider to be positive. So if I add them together, I'm going to end up with 0. So all of this area on top is going to cancel with all this area on the bottom when I subtract the bottom from the top. So I can use symmetry whenever possible if I recognize the integrand, so f of x being the integrand, if I can recognize the integrand as being even or odd, and I have a symmetric interval. So whenever possible, I want to use this notion of symmetry to simplify my calculations in evaluating a definite integral. Alright, so let's take a look at another example. Here we want to calculate the integral from negative 2 to 2 of the square root of 4 minus x squared dx using the interpretation of signed area. So this should look really familiar. We have the square root of 4 minus x squared. It was the last example we worked on, so we should know that this is the top of a circle, so it's a semicircle, and it's going to have a radius of 2. So we'll just sketch that out again really quickly. So we're going to have a semicircle with radius 2. But let's take a closer look at the limits of integration. This is a symmetric interval. I go from negative 2 to 2. And the square root of 4 minus x squared, well, that's a semicircle, and this function here, if I fold it over the y-axis, it's going to land on top of itself, so that makes this an even function. So instead of evaluating the integral from negative 2 to 2 of the square root of 4 minus x squared dx, well, I can evaluate double the integral from 0 to 2 of the square root of 4 minus x squared dx. And hey, we already found this interval, or this integral last time. It was just pi. So that must mean that this is now 2 pi. So 2 pi is now the area underneath the semicircle, the square root of 4 minus x squared, but we didn't have to do any other calculations or go back and do each portion of the quarter circle separately. We just doubled our previous answer. So 2 pi is the answer. Properties of the definite integral. So suppose f of x and g of x are integrable over ab and k is some constant. Then the first property we have is that the definite integral from a to b of f of x plus or minus g of x can be written as two separate integrals. So the integral from a to b of f of x plus or minus the integral from a to b of g of x. So we have the sum or difference rule. We also have the constant multiple rule. So if I have a definite integral of some constant times a function, I can pull out the constant and then evaluate the integral by itself. The next rule is really interesting. I have the integral from a to b of k dx equals k times b minus a. So I say that it's interesting, but really it's not even worth something that you should worth memorizing so much as just something you should sort of graphically understand. So if k is a constant, then the graph of this function is going to look like a horizontal line at k. So here's my line k. If I'm interested in the integral from a to b, so here's a and here's b, so the area under the curve from a to b of this curve, or this straight line k, I'm really looking for the area of just exactly one rectangle. And the area of this rectangle, well, the base is b minus a. So this distance here is b minus a. And the height, well, that's just k. So base times height, b minus a times k, that's exactly this. So here, all this is saying is if I take the integral of a constant, it's really the same as finding the area of a rectangle. This next property we're going to use very often. So this property says that if I am trying to evaluate the integral from b to a of f of x dx, where a is less than b, then I should rewrite this as negative the integral from a to b of f of x dx. So if a is a smaller number than b, but a's the limit of integration on top, the upper limit of integration, versus the lower limit of integration, then we need to switch the places, but to do that, we have to put a negative in front of the integral. So just as a quick example, if I have the integral from 2 to 0 of f of x dx, well, 0 is smaller than 2, so this is equivalent to negative the integral from 0 to 2 of f of x dx. So I always want the lower limit of integration to be the smaller number and the upper limit of integration to be the bigger number. So to make that happen, I need to switch the limits of integration but make the integral the opposite sign. So in this case, since it was positive, I needed to make it negative. The next one, the integral from a to a of f of x dx equals 0. That should be kind of intuitive. I'm not going anywhere. So from a to a, so there's not going to be any area trapped between the same number and itself, so that's just 0. And this last one we're going to use pretty often. It says if I'm computing the integral from a to c of f of x dx, then I can instead write it as the integral from a to b of f of x dx plus the integral from b to c of f of x dx if b is some number between a and c. So I think it's best illustrated with an example using numbers. So let's say I'm interested in the integral from 2 to 5 of f of x dx. Well, instead of evaluating this integral, I can instead evaluate the integral from maybe, let's say, 2 to 4 of f of x dx, and then add the integral from 4 to 5 of f of x dx. Because 4 is between 2 and 5. So it's like saying if I want the area between 2 and 5, well, let's first find the area between 2 and 4, and then add to it the area between 4 and 5, and I'll have the total area. So this is a property that we're going to use pretty often. Alright, let's look at an example. So here we're given the integral from 2 to 0 of f of x dx equals 2, the integral from 2 to 4 of f of x dx equals negative 3, the integral from 2 to 4 of g of x dx equals 4, and the integral from 0 to 1 of f of x dx equals 1. So given these pieces of information regarding the signed area of these functions f of x and g of x that I don't know explicitly, I want to use the properties of definite integrals to evaluate the following new functions that are modifications of these functions f of x and g of x over perhaps different intervals. So here, the integral from 2 to 4 of 2f of x minus g of x. So what I want to do is I want to use that difference rule and the constant multiple rule to break this up into separate integrals where I can use the two middle pieces of information I have here, because these two middle integrals have the right limits of integration that I'm looking for between 2 and 4. So we want to show all of our work here because we're being asked to use the properties of definite integrals. So let's write this as the integral from 2 to 4 of 2f of x dx minus the integral from 2 to 4 of g of x dx. So the first step was I split it into two separate integrals being subtracted. The next thing I'm going to do is pull out the constant multiple 2. So 2 times the integral of 2 to 4 of f of x dx minus the integral from 2 to 4 of g of x dx. And the last thing I'm going to do is go ahead and substitute in my values and simplify. So the integral from 2 to 4 of the function f was negative 3. So 2 times negative 3 minus the integral from 2 to 4 of g is positive 4. So I'm going to keep working off to the right to make space for the next problem. I'm going to have negative 6 minus 4 or negative 10 as my answer. So now let's look at the next example. I want the integral from 0 to 4 of f of x dx. So which pieces of information am I going to be using here? So I want to know what's going on between 0 and 4 of the function f. So here, this tells me what's happening between 2 and 0. This one tells me what's going on between 2 and 4. Well, here, a quick switch of the limits of integration and then making this one negative will help me evaluate the integral from 0 to 4. So this is going to take a few steps here. So the integral from 0 to 4 of f of x dx is the same as the integral from 0 to 2 of f of x dx plus the integral from 2 to 4 of f of x dx. Well, the integral from 2 to 4 of f of x dx, great, I got it. It's -3. We have that. But we don't have the integral from 2 to 0. We have the integral from, we don't have the integral from 0 to 2. We have the integral from 2 to 0. So what we're going to have to do is rewrite this as negative the integral from 2 to 0 of f of x dx plus the integral from 2 to 4 of f of x dx. So now we have negative, well, the integral from 2 to 0 was +2, plus the integral from 2 to 4 was -3. So -2 plus -3 gives me -5. So here I used two different properties of the definite integral. I used where I can switch the limits of integration as long as I make it the sign opposite in front of the integral. And I use the property that I can split this integral into two separate ones using any point in between 0 and 4, between the limits of integration. So now the last one, the integral from 1 to 4 of f of x dx. So what I want to do here is I want to use a clever manipulation of the last property. So I want to find the integral from 1 to 4. So what I'm going to do is I'm going to say, well, I know the integral from 0 to 4 of f of x dx. I know exactly what that is. I found it in the previous problem. So the integral from 0 to 4 of f of x dx is -5. But that's overcompensating. So that's more area than I want to consider. I only want what's going on between 1 and 4. So what I'm going to do is subtract the integral from 0 to 1 of f of x dx. And that piece of information I do have. It's the last part that I haven't used yet. The integral from 0 to 1 of f is 1. So what I'm doing here is I'm really using that last property, but a rearrangement of it. So instead, I'm taking the integral from 0 to 4, which is the same as the integral from 0 to 1, plus the integral from 1 to 4. So I'm just rearranging things here. But now, the integral from 0 to 4 is -5, minus the integral from 0 to 1 is 1. So here, we're going to end up with -6 as the area, the signed area between 1 and 4 of the function f of x is -6. The comparison theorem. So if we have two functions, f of x and g of x, and f of x is always less than or equal to g of x on some closed interval from a to b, so that means that f of x is below g of x on this interval, then the integral from a to b of f of x dx must be less than or equal to the integral from a to b of g of x dx. So in this picture shown here, the blue graph would have to be my g of x function, and the red graph would have to be my f of x function, because g of x has to be above f of x. So I need to choose a particular interval. Let's say that I'm looking at the interval from 1 to 5. So here, the area under the curve, in this case from 1 to 5 of f of x, so all of this area, if I go up to the function, I'm looking at all of this area here, that has to be less than the integral from a to b of the g of x function. Well, because g of x is always above f of x, now I have to go all the way to the g of x function, and I'm looking at all of this additional area plus the one that happens to fall below f of x. So this is just sort of an intuitive concept. If g of x is above f of x, then there's going to be more area under the function that is on top than there is area on the function that is below. This next piece is a bit of an extension of the comparison theorem, and what it says is if m is less than or equal to f of x is less than or equal to big M, so little m and big M in this case are constants, they're numbers. So if some function f of x is trapped between two numbers on the interval from a to b, then the integral from a to b of f of x is trapped between m times b minus a and capital M times b minus a. So I think that's best illustrated with a graph. So let's imagine this blue function here is my f of x function, and the red line on top is my capital M, and the red line on bottom is my lowercase m. So two constant functions. Now f of x is trapped between these two constant functions on the interval from, let's say, 2 to 4. So what this theorem says is on the interval from 2 to 4, I'm actually interested in the area that goes all the way up to the blue f of x function. So here's what I'm searching for, this area. But I know that if f of x is trapped between little m and big M on this interval, and it is, then I can say that the actual area between 2 and 4 must be between the area that is formed by taking the rectangle between 2 and 4 that goes up to the line M, so this amount of area. So remember that this distance here is 4 minus 2, or b minus a, and this height here is little m. So the area of this rectangle here is going to be b minus a times m. So I know that the actual blue area I was searching for, well, it's more than b minus a times m, or 2 times m, and it's less than, so if I go all the way up to the bigger m function, and I consider all of this area, well, that's way too much. So that's going to give me an over approximation. So the actual area, the blue area, is trapped between the smaller rectangle made by b minus a times little m, and it's smaller than the area of the bigger rectangle, which is this height here, this big M, times the width b minus a, in this case 4 minus 2. So the comparison theorem extension really is trying to tell us that we can trap the area that we're trying to find between two whole numbers that will be easy to find, because each of these on the left and on the right, these are just areas of rectangles. So it's kind of giving us a bounds, or a general idea of what this area would have to be trapped between. Alright, now let's take a look at some AP multiple choice questions. This one says if f and g are continuous functions, and if f of x is always positive for all real numbers x, which of the following statements must be true? So this first one says that the integral from a to b of f of x times g of x dx is the same as the integral of a to b times f of x times the integral of a to b of g of x. This is not a property of definite integrals. So we had that list of properties of definite integrals, and there's no such really product rule of any kind that works like this. So this one is not true. Number 2, the integral from a to b of f of x plus g of x can be split into two integrals. The integral from a to b of f of x plus the integral from a to b of g of x. That is true. That was one of the properties of definite integrals. So 2, part of the answer. 3, the integral from a to b of the square root of f of x dx equals the square root of, and then underneath the radical I have the integral from a to b of f of x dx. This was not a rule. This was not one of the properties of definite integrals. What they're trying to do here a little bit is trick you, because there are properties that we've learned about that do break up a product or a square root, but this first one and this last one would not apply to definite integrals. They do apply to limits. So if you're thinking that you've seen a property similar to this, it's true that this property works for limits, this square root property, and this product property works for limits, but it definitely does not work for definite integrals. So only 2 must be true. The other ones could be true for particular functions, but number 2 must be true no matter what. It is always a property of definite integrals, so the answer here is B. Alright, let's take another look at an AP question. So if the integral from a to b of f of x dx equals a plus 2b, then the integral from a to b of f of x plus 5 dx must be what? So here's what we're trying to find here. The integral from a to b of f of x plus 5 dx. Well, here I have two functions being added together. Now one of them is the generic function, just sum f of x, and the other one is the constant function 5. But since there are two functions being added together, I can split this up using my properties of definite integrals to be written as the integral from a to b of f of x dx plus the integral from a to b of 5 dx. Now, the integral from a to b of f of x dx, that's given. So the answer there is a plus 2b. So the answer to this first integral is a plus 2b. So now it's a matter of solving the integral from a to b of 5 dx. Now this too was a property of definite integrals. So the property was that if I take the integral from a to b of some constant dx, the answer here, well, we're really just finding the area of a rectangle. So the width of the rectangle was b minus a, and the height is the constant. So the constant here is 5. So the first integral, a plus 2b, was given. The second one I had to solve using my properties of definite integrals. So now we can simplify because this is not one of the answers. Without simplifying, I have a plus 2b plus 5b minus 5a. So combining like terms here, I have 7b minus 4a, and that is option C. So my answer to this one is C. And the next one we'll look at together, number 32 from a multiple choice AP exam, states that if a, the integral from a to b of f of x dx equals 5, and the integral from a to b of g of x dx equals -1, which of the following, again, must be true? So I'm actually going to work my way from the bottom up. I'm going to look at number 3 first. The integral from a to b of f of x times g of x equals -5. So if you look at what the problem is trying to say must be true, what they're really doing here is saying, well, is it true that we can split this up into the product of two separate integrals? Because up here I've been given each integral separately as 5 and -1. So they're saying, is it true that when I multiply these together, these functions together, and take their integral, it's the same as taking the integral of each independently? And again, the answer there is no, that that's not a property that works. So 3 doesn't have to be true. So which of the following must be true? Not 3. So 3 is something that I'm not considering as part of my answer. Number 2, the integral from a to b of f of x plus g of x dx must equal 4. Well, that must be true because the integral of a sum of two functions can be split into the sum of two separate integrals. So since the integral of f from a to b was 5 and the integral from a to b of g is -1, I can simply add the two solutions together to arrive at 4. So 2 is going to be part of my solution. Now number 1 is the trickiest one, I think. This one says, does it have to be true that f of x is greater than g of x for all the values x between a and b? Now, a lot of people are going to want to say, yes, this has to be true. Because they're thinking, well, the integral from a to b of f of x dx is a positive number. And the integral from a to b of g of x dx is a negative number. So that must mean that the function f of x is always above the function g of x, because that's what this statement means. F of x is greater than g of x. That means that f of x is above g of x. But we have to be careful. That's not quite what it means. If the integral from a to b of f of x equals 5, that just means that the signed area is positive 5. So let's go ahead and draw a counterexample to show why this is not always true. So let's say I'm taking the integral from a to b of some function f of x. So I'm going to go ahead and say, here's my function f of x. And here's the interval from a to b. So by looking at it, I can just go ahead and say that the answer to this integral is a positive number, and we'll say that all of this area is positive 5. Well, now I want to try to draw some function g of x that at some point is above f of x. So it doesn't matter for how many points, just at some point g of x is bigger than f of x for some value, but I still want the area between a and b of g of x to be a negative value. So I'm just going to go ahead and start my g of x function above f of x because I'm trying to draw a counterexample. So here's my g of x function. What I needed to do is I needed to dip down pretty low because I want to make sure that all of this positive area I'm accumulating, that I end up going further down to make sure that I ultimately end up with more negative area. So here's an example. This function here is my g of x, of g of x being above f of x for some point in the interval from a to b. So g of x over here is above f of x, but g of x is still ultimately, or the integral from a to b of g of x is still ultimately a negative number because there's more negative area down here than there is positive area up here. And f of x is still giving me some positive area. So here's a counterexample of why this doesn't have to be true. So 1 doesn't work, so the only answer here is B, 2 only.